exploring the intersection of resilient technology, organizations, and people. REdeploy.
I work at Netflix. I manage the demand engineering team. We focus on the global distribution of traffic and load and data for Netflix. There's 3 of us. In this talk, we'll talk about why I'm here, why I think this is important, algebraic models that are wrong but hopefully useful, and then eventually we'll talk about the architecture that will potentially enable all of this good stuff. All right, so why am I here? I'm here for 3 reasons. 1, I get super frustrated when the sites that I care about don't work, so I don't want that to happen. 2, I'm trying to increase my follower count because I'm super envious of Nora's digital points on Twitter. And number 3, we're hiring. So Netflix usually works fine, and sometimes it has a little bit of a trouble. And earlier on, things were going well. We had a 2-island model with 2 different regions, one in the North America, one in EU. And there was an ELB outage in Amazon. It lasted for a while. We were down for a while. And the perspective at that point was that this was unacceptable and should never happen again. It's amazing how the appetite to take on big availability projects increases through proximity to recent outages. So we had this island model, and we decided to spin up another region that would, in the beginning, only have proxies. And these proxies would allow us to use DNS to shift traffic to this basically empty region, and then use that proxy to go back to the other region that had the bad ELBs, but connect directly to the mid-tier. This would allow us to not be vulnerable to an ELB outage. However, we were still vulnerable to regional outages, and we wanted to make sure that that overall risk profile could be reduced. Started off by creating an active-active setup between 2 different regions in the US, with EU still as an island. And eventually, we reached our goal of having active-active-active, and this let us fail out of any region at presumably any time and still serve all of our traffic. Now, in the beginning, we were new at this. Whenever I've been new at anything, I haven't been very good at it. And the way that you get good is by doing more of it. Unfortunately, not being good in the beginning led to instability. And that instability led to fear. And that fear led to an infrequency. With an infrequency of running these failover exercises, it increased the likelihood that we would have introduced a regression into production, which meant the next time we ran it, there was a higher likelihood that it would be unstable, which meant there was greater fear, and so on and so forth. So we realized that fear was a little mind killer. It was the little death that brought total obliteration. So we decided to face our fear and lean into it, increase the frequency, despite the fact that there would be some momentary turmoil. Through routinizing the procedure, we were able to overcome that fear and build the culture of expecting that this would be something that would happen. Additionally, one of the things that we realized was that speed was extremely important, not just in terms of the business metrics, but also in terms of the people involved. In the early days, our failover evacuation took around an hour. And when something that potentially risky takes so long, you can have your spirits run so hot, you get exhausted, you aren't bringing your best self to the table. Additionally, as our service continued to grow, we realized that maintaining that long of an outage would be ever worse. So investing in speed was important both from a human perspective and also for a business perspective. So we pursued this project Nimble, which took us from 45 minutes at that point down to under 10 minutes. And now we can do failovers in around 7 minutes. The details of this are available on the Netflix blog. It's not relevant to this talk, other than the fact that we had this speed. Even though we had the speed, we still were placing a burden on different people who were involved in building and operating Netflix. When we would evacuate a region, people who had all of their diligently crafted alerts to have high regional awareness would get paged. If you're getting paged because one region is evacuated, you're likely to keep hitting the snooze button. And if you do that, you're not going to notice that, oh, East 1, East 1, East 1, US West 2, East 1, East 1, whoops. And so we ended up not being aware of potential issues because we had created this alert fatigue. Canaries were also regional. Having a region evacuated would fail the canaries, slow people down. We use a lot of week-over-week metrics, right, which is another way of trying to understand what's normal for the system. Well, if this week my load is twice what it was last week, what does that mean? Was there a failover last week? We induced this new cognitive burden. So it's not a free thing to do. However, we tried to understand what it would take to go from burden to advantage. So safety was the first thing I mentioned, in that we wanted to reduce the potential impact from doing a failover. Now when we evacuate a region, there's no perceptible impact to our customers, and almost nobody gets paged. And additionally, having the familiarity that this is just something that we do, this is normal, this is our everyday, led us to think about, well, instead of this being a disaster recovery mechanism, what if this was a rapid recovery mechanism? What if this was a tool in the tool belt that the operators could use? And what if it's not just regional evacuation? What are the other levers that we could pull? What does it mean to be able to shift traffic throughout the world? What does it mean to potentially drain a region slowly or quickly? And so in building our tools, we don't just have the evacuate tool, right? We have the tool that lets experienced operators in concert with the incident commander and other key partners make decisions on the fly. We don't love improvising because we make more mistakes, but having that capability has saved our tukuses quite a few times. So this is from the Netflix culture memo, and the first talk talked a bit about this when the difference between resilience and robustness was mentioned. I understand that resilience is fundamentally a human concern, but there are tools that we can provide to the humans that let them take actions of recovery as opposed to prevention. And in general, I'm a strong believer that investing in recovery is far superior to investing in prevention, because recovery techniques let you withstand sources of error that you couldn't previously perceive, whereas prevention techniques tend to require the programmer to imagine a certain kind of scenario or a certain kind of way that things could fail, and then go and make sure that that scenario doesn't happen. So for instance, using regional isolation for how we deploy our systems, for how we change configuration, for how we roll out data, means if somebody didn't foresee that some service 2 layers down in the stack was going to change its latency by 10% and that was going to cause me to be overwhelmed, it doesn't matter, right? I mean, it matters. We don't want to have downtime. But what it means that we have a total little group of isolation. So if something goes bad here, we have somewhere else that we can go. One analogy is that we still have to fight the fire, but at least we've evacuated the building. So now we're going to get into the models of what going into multi-region can do for your availability. And when I say multi-region, it doesn't have to be like the AWS notion of region. These are really applicable to potentially abstract failure domains or fault isolation. Basically anything that you treat as independent entities that you change differently, that have different risk profiles, different things they're exposed to. Regions are nice because they're isolated to different weather events. Our cloud provider does make regional changes, so it's nice to have that extra layer of recovery. So to achieve availability, we need to focus on the distribution of change. I think I've mentioned a few times that as long as we make changes regionally, we're able to use these tools and techniques to recover. If you make global changes, there's some things that we can do. We can use our overhead to try to increase our capacity, but it really limits our ability to use this set of techniques to recover. So maintaining isolation is going to be key. The next thing that comes into a factor about how going multi-region could impact your availability is the number of regions. If you have one region and it goes bad, it's 100% loss. If you have two regions, one goes bad, 50% until you can recover. 3, 33%, and so on and so forth. So just to have a quick model of that, it would be 1 over n plus 1 in an n plus 1 architecture, meaning you run with effectively 1 unit of spare capacity. So if you're in one region, n here is 0. So this whole n plus 1 versus n thing is kind of confusing, and you have to keep track of the extra 1, and that's throughout the talk, so I apologize, but it makes some of the other math easier. So as you can see, we have this law of diminishing returns, right? Because our denominator is growing. And another thing that impacts our availability is the balance of traffic. So if we had 3 regions, but 70% of our traffic is in one of them, and we lose it, we're not losing a third of our traffic, right? So thinking about what does it mean then to balance traffic, not in terms of total requests per day, but at each instantaneous moment. Okay? And we needed to come up with a way of comparing the availability of different traffic distributions. Let's say you have 3 regions and one has more traffic than the others. On a risk-adjusted basis, if all regions have the same chance of failing, then every traffic distribution has a same risk-adjusted expected stream loss. So streams are the thing that we tend to use as a measure. However, if you have 70% of your traffic and the region goes bad, that's clearly worse than having 33% of your traffic there and having the region go bad. So then there's this notion that we had that there's some form of excessive risk exposure, and we wanted to figure out how to quantify that. So when we wanted to figure out what the right distribution of traffic would be, we could have machines churn through and come up with a bunch of scores that we could easily compare. So I will translate this. The evenness is the most fair balancing of traffic. It's not the most efficient. The optimal balance of traffic would be that you only have failures in regions that are very lightly loaded. But we can't generally guarantee that. So maintaining that evenness is what we want to do. So this basically says for each region, for each hour of the day, take the max of 0 and the region's traffic minus the global traffic divided by the number of regions. So basically see how far above proportional we are, scaled by the amount of traffic that we have, is another way of thinking about it. So at Netflix, our traffic varies throughout the course of the day and the night. Fewer people watch it in the darkest times of the night, or sometimes in the early morning, compared to when they get home and they want to relax, et cetera, et cetera. So we can't just sum it over the whole course of the day and take the peak or something like that. It's really the accumulated excess risk that we care about. And that's what this summation does. Our traffic is not perfectly evenly loaded, so we needed another way to be able to conceive of what our risk exposure was. And we had an empirical risk study. So we took all of our previous outages, tagged them for the source of outage self-induced versus, say, a fiber cable gets cut, et cetera, et cetera, et cetera, to see if this sort of technique would potentially have mitigated it or reduced the impact. And we're able to play that back through new traffic distributions. And this let us get an idea for our distribution, what our risk exposure was. And that math is not fit on a screen. All right, so now we're going to talk about latency. One of the reasons that people think you should go multi-region is that you can put data centers closer to your customers. When you think about latency, there are multiple different parts that make up that full chain. Application rendering speed frequently is way larger than your network latency. So is moving a data center close to the person going to make an impact? Also, the last 5 miles of latency has a much wider variation than the variation you get once you're on the backbone from region to region. So the impact that placing regions close to your users can have is variable depending on your application, depending on how many calls and responses you have in your application design, and how latency sensitive your app itself is. Another dimension of looking at which latency is if you're going to have regional evacuation as a tool in your tool belt, you're not always going to have prod in the same mode. So we have normal mode, where we have the load roughly evenly distributed throughout all of our regions. And then we have failure modes, which is for each region that we take out of the participation of serving traffic, how does traffic get distributed? So it is my belief that the latency profile of your normal mode is what really matters to users. And as long as you aren't failing to satisfy requests in your failover mode, latency becomes less material. And then cost really comes into play, where you'd want to have in the failure mode, really lean into evenly loading. So this is just a way of visualizing these 3 different concerns that come into play when thinking about latency and traffic routing. The latency impact of having different regions also really matters on where your users are located. From an availability perspective, you want it to be evenly loaded. Again, n+1 is all of the regions, because you have 1 extra. And then cost is 1 over n, because you're going to have to be able to run with any one region being down, so you can have excess capacity then in each of your regions. So you can optimize for latency within the cost boundary and still have some room to play, if you will, at a potential sacrifice of unnecessary risk exposure. So this is just a quick little quip. The reason I present this is that the Pacific Ocean is quite large and not inhabited compared to the rest of the longitudes that we have. So it is very frequent that you'll have a dip. This will come into play a little bit later on when we talk about architectures. So like we had to come up with a model for measuring availability, we wanted to come up with a consistent score for latency. Latency is not a number, it's a distribution. Some users also have different tolerances for different kinds of latencies. People who are in countries with internet that isn't quite as refined as the experience that we can experience, say, in USA, would potentially have a higher tolerance for latency. When thinking about how to compare distributions, we wanted to be able to weight lower percentiles or be able to weight higher percentiles. So people are experiencing 95th percentile latency, 99th percentile latency. The difference in those numbers is more important to us than the difference at the 50th percentile, perhaps. So again, I'll translate. If we have our cumulative distribution functions, our distributions of latency, and we sample them at multiple points, we can then take those samples and just do a simple subtraction. So P here is an array of percentiles that you care about. CDF-A would be one potential steering configuration. CDF-B is another. And you just sample at multiple points and diff them. Or you could sample at each point and diff and then sum the differences, because it's commutative. And if you add more and more percentiles that you sample at a higher point, that kind of like weighs that part of the curve. Now, that's theoretically great, but in practice, this does pretty much the same. It's within a couple percentage points of difference to end latency. So, you know, this was really cool, though. We were so proud of it. All right, cost. So, I presume you all care about availability, and you want to go to the person who potentially signs checks and say, hey, I saw this talk, Aaron Blohowiak is amazing, I follow him on Twitter. I want to go multi-region. They're going to be like, what's that going to cost? So by show of hands, who thinks we can go multi-region for less than double our cost to be in one region? One hand? Two hands? Oh, all right. Lucky you. Lucky all of you. So before we get into the punchline of the joke, we have to, when we're going to compare costs, we have to have a basis for comparison. So I'm going to say if you run currently in one region, that's 100%. So we're going to be able to experience potentially 200% cost, okay? Additionally, that 100% is broken up between the amount that's throughput-based, in that it scales or could scale down if you reduce the throughput required in that region, and a proportion that's fixed cost, I'll call that the database portion, but it can be more things than just that, which are required to serve a region. Additionally, n+1 architecture. I think I've explained enough times that this weird 1 or n thing we have to carry around. So again, n+1 is the total number of regions. So in an n+1 architecture, the minimum failover overhead is 1 over n. So if you have 3 regions, any 2 need to be able to support 100% of global instantaneous demand. So that means 2 equals 100, so 1 equals 50. 50 times 3 is 150, right? So the total cost then for pure throughput basis would be 100% plus 1 over n. So what this means is as you add regions in a theoretically pure throughput-based system, you're saving money. So if you had no database cost, then you'd want to just add as many regions as you could tolerate from an ops perspective. And eventually you'd want to consider the likelihood that a single region experiences an issue, because you might hit diminishing returns from an availability perspective. So this is now we're getting to this complicated thing with its database portion comes into play, because I don't think anyone has purely throughput-based scaling. And when we talk about this database portion, we have to figure out how many copies of your data you're going to keep around. The simplest architecture is to have all of your data everywhere. So let's start with that. So that all data everywhere, we'll call that a region replication factor. And so I'll say RF equals all. In this scenario, we have our throughput cost, which we talked about, that has this nice sublinearity as you add regions. And we can have to remove the database portion out of our 100%. So we're just adding up the throughput-based cost as we add regions. And in RF equals all, the D will be the database cost, and that will increase with the number of regions. It's just your database cost times how many regions you have. So our blue line here is if our database cost is 0. That's what we just saw a couple slides ago. And that's our theoretical minima. And we have a variety of lines just to show what the result would be depending on the proportion of your single region spend is your fixed cost. So at 5%, you get a sublinearity to 4 regions, even to 5, and then you start to scoot up, and so on and so forth. So it really depends on your application and the ratio between throughput and data cost, how many regions would be most cost efficient. Now we want, from an availability perspective, to go further to the right on this graph. So there's a bit of a tension between cost and availability. If we can have our region replication factor equals 2 and only have 2 copies of our data, well, now we get the sublinearity of adding regions, and we have a fixed database cost. So this lets us just almost purely realize the benefits of sublinearity of adding regions. So if someone who wears suits to work asks you, how much is this going to cost? You could say, well, if we invest a lot of engineering effort into it, we could be at less than 50% overhead and drive our availability, instead of losing 100% of our customers, to whatever 1 over n+1 at like 6 is. So that's potentially really good news compared to how many people here thought that it would cost more than 200% to go multi-region. So again, we can just go like, ooh. So we don't run with RF equals 2 at Netflix, but it's interesting. And we'll get more into like why we are where we are today in a little bit. So from a cost summary perspective, 50% throughput overhead plus a triple database cost gets you 3 regions with all your data everywhere. 25% throughput overhead plus double database cost gets you 5 regions with RF equals 2. Now, how do you do that? You gotta have your changes be regionally isolated. I have stressed that like 1,000 times. I'm gonna stress it probably 1,000 more. But without that, this whole kit and caboodle is just spending money. You wanna have it so that you have your stateless services, which hopefully have that sublinearity with throughput. And your stateful services will wanna have asynchronous replication. If you have synchronous replication and a region goes bad, you're not going to be isolated throughout the rest of your deployment. Additionally, a lot of us have like expensive persistence tiers, and then we want to have things be fast, so we put a cache in front of it that doesn't have all the data at the time. That cache hit rate then becomes a measure of efficiency of adding that cache. If you are going to move traffic away from one region into another region, and the caches are all cold, well, now that would necessitate increasing your spending on your persistence tier. So medium fancy math involved. We replicate the majority of our caches globally. For some things, it tends to actually be cheaper to increase the spend on the database. But that's why these models are not accurate, but they're hopefully useful. Again, one region at a time. Cross-region requests also break that isolation. So the whole arf equals 2, arf equals all is sharding or not, or the opposite. And that's like the main question that's just going to drive your architecture decisions. Steering. With all of our data everywhere, we can send any user to any region, and they'll have success. That's amazingly powerful. It's also amazingly simple. We don't have any consciousness of who the user is when we're sending them to a region. We know where they're coming from, and we can steer them based on that. But we don't have to know who they are. Our applications aren't aware of steering. It's all handled at DNS or at SSL terminating proxies that are deployed in our CDN. And none of that infrastructure has to be aware of where users are or where their data is. I got a bit into this in terms of how we steer, but rehoming and rebalancing can be really, really hard if your data is only in 2 places. Now you have to know, okay, what's all the data I need for this user? Let's move it somewhere else so we can rebalance all of our regions so we can maintain these cost and availability efficiencies that we want. That's not insubstantial. You can talk about clumping groups of users together and have many, 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 many shards, and then move a shard at a time. But then what happens if someone moves a significant distance? They may be routed into their home shard in a latency inefficient way, if latency matters. The cost we talked about, the yay comparison. Another thing is satellites. We'll get more into that a bit later. And the final thing is graph versus multi-tenant. So at Netflix, you have your account and multiple profiles. That's all kind of considered one group of data. But your data and your data don't really have a lot of interconnections. So it's very clear we have a nice aggregate route, if you're into domain-driven design, by which we can shard our data and talk about rehoming and rebalancing. If you operate a more graphed kind of application, it can be really hard to figure out the right way to do arf equals 2. So how do you do RF equals 2 with 1 over n overhead? If you say, oh, I just want to have my data in 2 places, the simplest version would be only 2 data centers. We already saw that that's 200% cost. If you say, oh, I'll do 4 data centers with 2 copies of, say, active-passive, well, now you actually just have 2 silos of 2 data centers. And that's also going to be 200% cost overall. So we got to get tricky. So there are 3 ways, only talking about 2 of them. I think you should be able to infer how the third would work afterwards. So universal savior. So in this model, we have 4 regions that you could conceive of as owning that chunk of our data. And then a 5th region, which has a copy of each of the 4 other regions' data. So now any single region could fail, and there's another region which could take over. And the overhead that we have to have in order to support failure modes, which is that center region, if you will, in this model, just has to be sized large enough to be equal to the next highest ring, the next highest, largest region. So if you do want to get into imbalancing your regions for latency purposes or other reasons, you can constrain the cost. And this is that satellite thing I was talking about. If you want to spin up a small region that isn't the same size as the others, you can just bear the cost of the additional throughput overhead for that region without having to have additional costs ripple throughout your whole architecture. That can potentially be powerful if you have a group of users that lives on a big island in the middle of the ocean. So here is the second architecture that you could potentially use for RF equals 2, which is ring regions. I should hire or have someone who's good at creating graphics create a different version, but I hope you'll bear with me. So here we have 4 different sets of data, just like we did previously. And you can conceive that there's The active-passive pairs, potentially, but not really. They will want to be active-active, but you have two copies. So you have the blue, the purple, the orange, and the green. The outer ring represents regions. So each region has basically a left set of data and a right set of data. And my right would be my left now, you know what I mean? All around in a ring. So if our yellow region goes bad, now we still have this nice property where there is a region that can handle each of our different sets of data. In terms of trying to conceptualize how the load would work in that scenario, well, each of the slices of the rings then grows to encompass it. But the regions aren't taking on new sets of data. They're really still covering the same color of data that they were previously. So we can see that we can have this RF equals 2 with an equal participation among all the different regions. Adding a satellite region in here doesn't really work. It messes up some of the math about how things work. You could maybe sneak in a new wedge, but it's really complicated. The hashing technique would be if you were to take each person's data and you were to replicate it to another region, but instead of here where blue is all the blue ones are replicated to another all blue one, it would be replicated randomly throughout all of the other regions. The user steering for that gets really complicated and messy. Before I get to this, yeah, so the reasons why we have not yet pursued RF equals 2 has to do with that additional complexity that you'd have to bear. And it's not just that the code that you'd have to write, it's the operational complexity. Right now, we roughly know which geographies go to which region in which failure scenario. If we had to be more aggressive in steering and in steering specific users, that sort of intuitive sense that the people who operate the system have developed would be lost. There's a huge potential advantage for cost efficiency, though. So weighing that person burden and the operators versus the business goals is something that we're going to have to look into. It also opens the opportunity to come up with clever solutions for how we could potentially reduce that operator burden by creating ever more complicated screens or views or slightly erroneous models of how the system works. So closing thoughts, to quickly summarize, follow me on Twitter. Multi-region is way less expensive than all of you thought. Yay, that's a great result. It doesn't have to be hugely complicated if you can replicate all of your data everywhere. And you should do it. It's good for your users. It's good for you, because you can evacuate the building while you're putting out the fire. And that's all I have.